And now let me mention a corollary of Minkowski's linear form theorem that will be frequently used in applications. In this corollary, instead of using those ones for inequality, we're going to put any scalars in here as long as the product of those scalars is equal to plus 1. So this corollary will be you still have a matrix m plus n by m plus n with determinant plus minus 1. Then there exists a non-zero integer vector such that a of this vector is equal to y, with y satisfies those inequalities. The first m components will be less than or equal to alpha sub j's, and the last n components will be bounded by alpha sub k's, with the product of those scalars equal to plus 1. And of course, you have to assume that each scalar is positive. You should be able to see this corollary immediately from the Minkowski's linear form theorem, but if you don't, let me still prove it anyway. The trick is that we are going to replace A in Minkowski's linear form theorem by as follows. If A is written as a block matrix with rows A1 through A sub m plus n, then you take A underlined to be this matrix. So this underline A will play the role of A in the Minkowski linear form theorem above. So by the theorem applied to underline A, so here keep in mind that the determinant of this underline A is still plus minus 1, because the product of 1 through m plus n is 1. So the determinant of this is still equal to plus minus 1. So apply to this matrix, and the vector y underlined, which has components y1 underlined through y m plus n underlined. This is just defined to be y1 divided by alpha j through ym plus n divided by alpha m plus n. And the Minkowski's linear form theorem tells you there exists a non-zero vector x that is integer valued and non-zero such that the underline a applied to x is equal to the underline y. So here those y sub j's will satisfy the original boundedness condition for those components of y. And this gives you, if you write this back to the what we have at the beginning, and you clear the denominators on both sides, this gives you what we want. And this completes the proof of this corollary.